Welcome to The Explainer. Today, we're tackling something, well, it's pretty mind-bending. What if I told you that your thoughts, your memories, even those sudden flashes of intuition actually have a shape, a specific mathematical structure?
So let's just jump right in. This is the big mystery we're exploring, all based on the work of Torsten Asselmeyer-Maluga. And the question is just massive. How does this mushy biological hardware we all have in our skulls produce something as complex and abstract as a flash of intuition?
All right, here's how we're going to break this down. First, we'll look at the deep structure of the mind. Then we'll talk about loops and holes and how they create thoughts. After that, we'll see how learning changes everything, what makes intuition different, and finally, we get to a literal fractal signature of the mind. Let's get into it. Okay, section 1, the mind's deep structure. The core concept here is pretty simple but profound. It's not just about what the neurons are, it's about the shape they make together. Yeah, so the key isn't zooming in on one single neuron out of billions. It's about zooming out and looking at the qualitative shape of all their connections. The secret isn't in the bricks, it's in the architecture of the entire building. And that architecture has a special name in math. That field of math is called topology, and it's kind of weird but really cool. See, topology is all about the theory of shapes, but it doesn't really care about things like length or specific angles. All it cares about are the fundamental properties that don't change when you stretch or squish something, as long as you don't rip it or glue bits together. This is the classic example, and it's just perfect. A donut can become a coffee cup. Why? Because topologically, they are the same thing. You can imagine squishing and stretching the donut, and the hole just becomes the handle of the cup. That single hole is preserved. But you absolutely cannot turn that donut into a solid ball without destroying the hole. That hole is the essential feature that topology cares about. It's stable. So, loops, holes, and thoughts. How do we take that coffee cup idea and apply it to our own minds? Because this is where we get to the actual building blocks of our mental world. Okay, so just picture your brain. It's this massive network buzzing with signals. And a lot of these signals form what we call feedback loops, right? They circle back on themselves. And these loops are what we're going to focus on. But here's the problem. The connections in our brain are constantly changing. So if the wiring is always in flux, how can any thought be stable? I mean, how do you remember your own name if the neurons that hold that memory are different today than they were a year ago? It feels like a paradox. And this is where that donut hole comes back in. Imagine a loop of string on a solid disk. You can just shrink it down to a single point. It's unstable, it disappears. But what if you poke a hole in the middle of that disk? Now, if the loop goes around the hole, you can't shrink it to nothing. It's caught. That loop is now stable because of the hole. And that is the big insight here. Stable thoughts are encoded in these non-contractible feedback loops. They're the ones caught on those topological holes in our neural network. They are the fundamental, unshrinkable patterns that give our minds structure. And just so you know, this isn't all just analogy. There's some pretty heavy-duty math behind it. This SL2C transformation is basically a language that describes everything about a signal, its strength, its frequency, its phase, all at once as it travels along these loops. This is the math engine that makes the whole model work. Okay, so that's how thoughts can be stable. But what about learning? How does this model explain what happens when we practice something over and over, and it goes from being hard to being second nature? Well, think about it. When we learn, what are we doing? We're sending signals with high amplitude and high frequency through the network again and again and again. You practice that guitar chord, you study that vocabulary word. You're strengthening a specific pathway. And here's where it gets really cool. The model says that when you do this, when you maximize that signal's strength and frequency, the network graph actually degenerates. And degenerates here just means it simplifies. It collapses from a messy web into a clean, simple tree. So you start with this complex web-like network of signals, but as you strengthen certain pathways through repetition, that whole signal flow just collapses. It becomes a simple branching tree. And the leaves on the end of that tree, those are distinct concepts. This is how your brain goes from, that's a flat thing with legs, to knowing instantly the difference between a table and a chair. So learning in this model is basically a two-step dance. Step 1, you increase the number of feedback loops and their connections. Step 2, you increase the signal strength through sheer repetition. You build the network, then you trim it down.
Right. So learning is all about simplifying things into a nice, neat tree. But what about intuition? That spark, that aha moment. That's not just making a path stronger. That feels like something else entirely. It's about creating a new idea.
So what happens if we keep the loops themselves the same, but we change the relations between them? What if we don't just walk the same path faster, but we actually bend the map itself?
And this is the crucial difference. Learning is about strengthening signals, which makes the network to generate into a tree. It's great for separating existing ideas, but intuition, that's about changing the loop relations, which means the tree itself deforms. It's not about making one branch stronger. It's about bending the whole tree to connect two branches that were never connected before. And that's how you create truly new ideas. Okay, so this brings us to the final piece of the puzzle. And honestly, it's the most mind-blowing part. We've talked about how the mind learns, but is there a visible pattern, a signature that shows a mind has actually learned something? It turns out there is. When the network has successfully learned, when those signal paths have formed that perfect tree structure, a stunning pattern emerges at the endpoints, right at the very edge of knowledge. The endpoints of that signal tree, they all come together to form a complex, closed shape, and that shape is a fractal curve. Think about that. A fractal is a signature that the learning process is complete and the information is ordered. If you have just a messy, non-fractal pattern, it means the information is still jumbled up. But a clean fractal, that's a sign of intelligence.
Which brings us to this incredible quote: "Mindless rules will generate mind." I mean, just let that sink in. The idea that from these simple, almost mindless mathematical rules about shapes and holes, something as complex and beautiful as the human mind can just emerge, it makes you wonder, doesn't it? What else out there is being shaped by these hidden patterns?